Welcome to this video. This is Pengfei from Clemson University. In this video, I will present my work published on CCGrid 2020. The work is entitled as Indicator-Directed Dynamic Power Management for Iterative Workloads on GPU-accelerated Systems. This is a cooperation work between Clemson University and Pacific Northwest National Laboratory. First, I want to give an overview of this work. This work is trying to address the power challenge for HPC systems. Power consumption is one of the major challenges that impact HPC involving. Our approach is trying to leverage the resource trace as application performance indicators, and we are trying to online and transparently predict optimal configuration for GPU workloads, either under a power budget or maximize energy efficiency. We summarize our contribution as follows. We develop an online power management framework for GPU systems. The framework can save 30% energy with performance requirement and can increase 10% performance under a power budget. We also propose a global performance indicator by monitoring the resource utilization trace. The HPC system is facing a big power challenge. In the last decades, the performance of HPC systems has increased over 1,000 times, and the power consumption also increased a lot. Today, the number one supercomputer, Fugaku, delivers more than 500 teraflops, but the power consumption of Fugaku is also very close to 30 megawatts. The very high power consumption requires expensive power supply infrastructures, and it also generates big burdens to power our grid. It will also require expensive cooling equipment, and the operation cost is also very high. So we can conclude that power consumption is one of the major challenges for HPC development. To address such challenging, we need to develop power management framework for HPC systems. In today's supercomputer, 6 out of 10 are equipped with GPUs. And the GPU contributes more than 95% of the computational capacity. And also it consumes more than 80% of the dynamic power. Power consumption among different GPU workloads are also different. Their variance can vary among 20% to 100% of the designed power limitation between different workloads. Power management for GPU workloads is necessary and also has the potential to improve HPC energy efficiency. To develop such a power management framework, we identify the following requirements. The framework must understand the impact of power bound on performance, and it can maximize the energy efficiency with performance requirement. The power management framework must be online and transparent. It can identify the optimal configuration online fast. It should be non-intrusive for security concern and easily deployment. In this work, we focus on iterative workloads. Iterative workloads are widely and commonly exist in HPC fields. For traditional scientific workloads, the simulation requires thousands of iterations, and the numeric calculations also requires a lot of iterations to get the required accuracy. The deep learning workloads also has thousands or tens of thousands batches in training phase and more batches for interference phase. The iterative workloads has the following features. The major runtime and power consumption is determined by the iteration stage. Between different iterations, the computation is stable. If we can identify the speed up and power of an iteration and apply it to other iterations to find the applications and performance and power relationship. Here we analyze the running behavior of an iterative workload called MD. When the user submits a job that's running CoMD, the CoMD will first initialization, such as reading data from disk, pre-computation some parameters. After the initialization is finished, it will go to the major computation, which is composed by thousands of iterations. We here draw the trace of the power consumption of the iteration stage. We can say the iteration stage power consumption shows periodic patterns. If we can build the relationship between the performance and the resource trace pattern, and we keep collecting fetch data and use this data to predict the optimal configuration for power efficiency and performance requirement. If we find such an configuration and apply it for the following configurations, the major iteration stage are running under the optimal configurations, which can save a lot of energy. Based on this idea, we developed this framework. The user submits the job with performance requirement. After the application passes initialization stage, we will do profiling online, and we will extract the PR rate from the application and build the relationship between the resource trace to application speed up. With a few examples, we can use speed up and power prediction to predict all configurations, performance, and power, and we identify the optimal configuration that meets the performance requirement or system power bound. We can even run the suggest config and validate whether the configuration meets our requirement. Here we can start from the initialization stage. We can say that the initialization stage is significantly different from the major computation stage. After that, we can online profiling the system and collect the data and do the peer extraction. Here we enlarge the trace of the CoMD. We can say in each iteration, there are two major phases, redistribute and force. The force have a lower computational intensity compared with redistribute, and we can say that the power consumption is also lower compared with redistribute. As a result, the trace is showing periodic patterns. We can use FFT to extract the PR rate from the resource trace. Here is showing we extract the PR rate for each trace, the power consumption, the GPU utilization, and the GPU memory utilization. And the last one is all the combined trace we extract the PR rate. After we extract the PR rate, we need to build the relationship between the speed up and the PR rate, and also the relationship between power and the trace. Here is what we have measured on different GPU frequency. We can say that under different frequency, the PR rate is also different. We use a relative speed up. We can say relative speed up matches very well with the extract pure rate. This proves that we can use the resource trace pattern to as indicators of the performance and power consumption. Here is our results for different applications. Both includes both deep learning application and HPC scientific applications. The average error for the applications is 3.4, and it also works well for different GPU accuracy. This allow us to use the resource trace as indicators for application performance. But we cannot measure all configurations. As we have discussed, there are almost 500 configurations for NVIDIA Titan XP. We can only use a few sampling configurations to predict the best configuration. For such a model, we think the inputs should be obtained online and it only requires a few sampling configuration. We consider the following models: analytic model, which will require multiple profiling samples for accuracy; machine learning model, which can use patterns that are shared among similar workloads, but it requires large offline training data sets. In this work, we propose AM plus machine learning. The AM can warm up the machine learning model, and it can decrease the profiling requirement and have better accuracy. After we find all the configurations, performance, and power, we can identify the one that either meets the performance requirement or system power bound. In this work, we considering two scenarios. One is application running in with a performance requirement. One is increased performance under a system power bound. First one, save energy with performance requirement. Here I show two examples. First one is low performance constraint. The second one, the bottom picture, shows the constraint that the application performance should be low larger than 10% latency, considered with the highest performance. Our proposed method can save 30% energy compared with the default, which has low configuration, just like the highest performance. The second scenario is maximizing performance under a power budget. Here we set a power budget for 160 watts. We compared it with the default 12 NVIDIA SMI. We can say our proposed method increased 10% for performance. Because there is a little bit of variance on the period extraction and prediction, our method has a case that surpasses the power budget by over 1 watt for inception 3. This error can be ignored because it's too small. So here I summarize our work. The interactive workloads shows periodic patterns. These patterns in system behavior can be served as application performance indicators, and we can build a relationship between these behaviors with application performance and power consumption. We use FFT to extract the pure rate from resource utilization trace. And we need some additional processing and validation. After we find the optimal configuration, we can also use such method to validate whether it meets the configuration. We use analytic model and machine learning to improve prediction accuracy. Such a model will decrease the training requirement and improves accuracy for both power consumption and performance prediction. As a result, our framework improves energy efficiency and maximizes performance under a power budget. Thank you for watching this video. If you have any further questions, please contact Dr. Wang Ji. If you are interested in our group's work, please feel free to visit Scale Lab. Thank you for watching this video.